Can you see it?
Yes.
Okay. It's 1628. Okay. Today I'm going to talk about the atomic debates and how noise settled them. I will try to go through it with a chronological order, and then I'm going to dive into the other effects of noise in the science. The idea of atoms goes all the way back to this man, Democritus, the philosopher himself. He put forward the hypothesis that all things, all materials, all matter, are constructed of small things that the human eye cannot see, and he named them atoms. Unfortunately, he is not deemed among the scientists who founded the atomic theory, since he did not explain anything with the existence of atoms. However, it is important to note that the whole atomic debate started out with his hypothesis. The prominent idea for the longest time was that all matter was made up of 4 fundamental elements: water, air, fire, and earth. Robert Boyle and Isaac Newton had formed the repulsion theory, which suggested that the air had pressure because the particles were somehow repelling each other, hence the name repulsion theory. Daniel Bernoulli tried to explain how they repelled each other and came up with the explanation that some little balls in the air could hit the sides of a box, creating the air pressure. He explained the air pressure with balls, which shows that Bernoulli believed in atoms. 4 fundamental elements were thought to be indivisible, but Lavoisier refuted this argument by showing that the fire was as a result of combusted, fired up oxygen. He also decomposed water, so showed that the fundamental elements were actually divisible. Lavoisier is known as the founder of modern chemistry because he found out that the conservation of mass law and the law of definite proportions, which are closely related to atoms. Which is why Dalton quickly understood that these were related to atoms, these laws were related to atoms, and he proposed his famous atomic model. Gay-Lussac was studying how gases with different volumes were combined during that time. Avogadro tried to put these 2 studies together and proposed that any gas with same fixed volume would have the same number of atoms, even if their masses are different. His proposition wasn't taken seriously at the time, but this number would be revealed to be Avogadro's number 100 years later. At the earlier days of the debate, heat was considered as a fluid. Rudolf Clausius thought otherwise. He defined temperature as a measure of the kinetic energy of each atom. Maxwell then later changed this definition with the help of Small problem. Small problem goes like this. If the first estimations of the gas molecules, of the speed of the gas molecules are true, a smell from a corner of a room should travel instantly to another corner, but this isn't the case. Maxwell claimed that the molecules were actually that fast, but they were colliding into each other, resulting in a reduced speed. Maxwell also argued that all particles have different speeds, varying from 0 to infinity and distributed accordingly to distributed Gaussianly. This led to the definition of temperature changing into being proportional to the average kinetic energy. Boltzmann realized that the speed of the particles evolve into a Maxwellian distribution and stays Maxwellian. However, conservation of energy dictates that things return to how they were. From here, Clausius coined the term entropy, which can mean disorder. And he said that entropy would never decrease in a closed system. However, Loschmidt, a friend of Boltzmann, claimed that if the positions of and velocity from a future time is known, since the Newtonian equations can be reversed, the entropy can also be reverted. Poincare later proved this to be true, and that the entropy goes back to where it was with enough time. Boltzmann couldn't refute this idea, I think, with his time, but there may be some discussions that entropy is actually real and never decreases, but I'm not sure about that, so I'm going to. Brownian motion is named after Robert Brown, but he thinks that the inventor of the microscope, Antoine van Leeuwenhoek, may have observed this motion before him. Brownian motion is the erratic, disorderly movements seen in microorganisms, pollen, or the inanimate objects. Robert Brown observed this in lifeless objects and suggested that it wasn't caused by a life force. Einstein, let's go to the miracle year. Einstein observed that the same number of particles in a suspended liquid produced more osmotic pressure than the same number of molecules, whereas in theory, the particles and molecules should have produced the same osmotic pressure. And he thought this was because of heat produced by the molecular motion. He said that if this motion was observed, it would prove the existence of atoms. And Perrin proved this. Einstein also provided a way to determine Avogadro's number, and I think Perrin also provided various ways to calculate Avogadro's number too. Maxwell's equations explain the relations between electricity and magnetism. Maxwell also thought that the light was an electromagnetic wave, and Hertz proved this. Most well-known Maxwellians are Hertz, Poynting, Fitzgerald, Larmor, and Lodge. Maxwell and Maxwellians solved many problems during the rise of electricity when Tesla's AC and Edison's DC were in the middle of electric wars. Speaking of AC and DC, John Fleming invented the vacuum diode as an AC to DC converter. De Forest added a grid between the filament and the plate. This allowed to control the electron flow and served as an amplifier. And the amplification formed the basis of modern communication. Vacuum tube is the ancestor of the modern day transistors right now, and semiconductors are closely studied because of noise. Schottky defined shot noise as the random fluctuations about a mean that add up to zero. You can see here as an example of shot noise. Randomly transmitted balls in a vacuum tube causes the shot noise, and this proves the existence of electrons. In a conductor without any, even in a conductor without any applied voltage, shot noise causes momentary currents, and this is called thermal noise. You can understand from its name, it's proportional to the temperature. Hubble Space Telescope discovered that the galaxies were straying away from each other. This led to two different schools of thought, two different theories. One of them was Gamow's Big Bang theory. He claimed that at the beginning, at the inception, all of the matter and all of the energy were concentrated at a small point-like space. Hence, it was very hot and it was very light. This would mean that if the galaxies are straying away from each other, there should be a small radiation that all matter radiate. This wasn't proved until 1940s when Bell Labs antenna measured the noise everywhere where it shouldn't have pick up any noise. They went to Gamow, and Gamow understood that this was the proof he wanted to, explain Big Bang theory. The mathematics of noise can be divided into two approaches. One of them is the Langevin approach, which tries to simplify the Einstein equations and easily finds specific moments of a particle, like mean and variance, with a stochastic force acting on it. However, it does not obtain the probability distribution. The other approach is the Fokker-Planck method, which intends to find a differential equation for a probability distribution changing in time, but it cannot be obtained from a Langevin equation. Karl Pearson created a problem where a man walks a fixed distance in a straight line, rotates at a random angle, and walks the same distance, then repeating this. After a while, when the walk ended, let's say n times, the probability that the man's position was in a given window of distance from the starting position is asked. This was the problem. Rayleigh solved it. Smoluchowski found the relation between the random walk and the Brownian motion. Random walk theory is now prominently used to describe stock market and finances. Later, Keck expanded the problem. Match filter, as you can see, let's say we have a signal and we add some noise to it, like in natural order, no signal is without noise. So let's say we add noise, and the match filter smooths it out and then samples it and tries to detect the original signal from it here. And match filter is still used in radar and sonar systems. Around 1850, Kirchhoff and Bunsen discovered that the molecules have unique spectral lines, just like every human being has unique fingerprints. Spectral lines being unique to the molecules led to easily identifying which molecules were present in a planet, moon, asteroid, or any planetary body, with only just observing from Earth with telescopes. Spectral lines have noisy widths that's affected by various environmental factors in the planetary body. Pathological functions. In the background, you can see Weierstrass's first pathological function that's very, very famous. On the right side, upper right, you can see the equation, and the animation is as n goes from 0 to infinity. As you can see, it looks very much like fractals. Prior to Weierstrass, it was thought that continuity and differentiability suggested each other. However, Weierstrass constructed the function on the upper right that is continuous at every point, but differentiable at none. These kind of functions are named pathological functions, and their popularity led to the fractals are everywhere moment. The most famous fractal is the Mandelbrot set. Jean Perrin was the first person to speculate that Brownian motion may be pathological, and Norbert Wiener proved this to be true. Pathological functions later led to the birth of super-infinites. Main problem of Fourier's time was the heat equation, and he derived it. While exploring other ways to obtain the heat equation, he discovered that any function, particularly the functions with jumps, could be represented as a sum of sine and cosine, as you can see here. This is now known as the Fourier analysis or Fourier expansion. Fourier expansion revealed that heat transfer is not a smooth transition, but a function with a jump. Dirichlet later set the sufficient conditions for a function to have a Fourier expansion and defined a few functions that don't have it. Quantum mechanics is different than classical mechanics. It is probabilistic and introduces us a new noise called quantum noise. Even though quantum mechanics is probabilistic, quantum probability is different than standard probability theory because it deals with operators and wave functions instead of classical functions. In quantum statistical mechanics, we have two probabilities. One comes from the waves function, the other comes from ignorance, and it works like classical probability. Let's say our two entities have these expectation values. In quantum statistics, which entity is going to be used is also probabilistic. So we have the probabilities for it too. Let's say them, let's call them P sub A and P sub B. And as a result, we get this expectation for the system. Dirac and von Neumann unified classical and quantum probabilities by creating a new construct called operator density matrix. As semiconductors are sensitive to quantum noise, and we live in the age of semiconductors, the study of quantum noise is very important. The invention of laser and maser developed quantum noise into an advanced level. Despite actively being researched, many theoretical and physical problems of quantum optics are still unsolved. Schrödinger solved the potential of an electron of a hydrogen atom in a vacuum quantum mechanically and verified his results with experiments. But later experiments have shown that the vacuum is not actually a void and has a fluctuating electromagnetic force. Deriving a proper quantum mechanical Langevin equation or Fokker-Planck equation and defining autocorrelation functions for operators has not been possible yet. Thank you for listening.